our RI seminar here. It's pretty clear that Seth is highly regarded by our department. That's why we had to come into this bigger room, because we couldn't fit into the normal seminar room. People here, of course, are starstruck by Seth. You know, he has had quite a broad and interesting career in the robotics science realm. Pretty much he hits almost every topic and then does it with great depth. But in addition to the great research that he's doing, he also has worked on some nice educational activities, most notably these 3 textbooks that he has co-written. I used 2 of them in 2 of my classes. It's a good book. I'm a co-author on one of them. Apparently I'm not doing a good job promoting this to my department.
Our royalty split is not even.
And it's not big either. That's why we're famous for going to McDonald's a lot, because that's what we can afford. Yes, so a lot of times when people come up to me, new graduate students come up to me, the first thing they say is, oh, you're in that McDonald's page, which is really not the best thing a grad student should say the first time they meet a professor for work. But if you do care to see where Seth and I have gone all over the world for McDonald's, go to sethandhowie.com. And that code is written in our textbook, in case you forget sethandhowie.com. But moving along to Seth's career, in addition to the research education, he's also held leadership roles. First one he was at the University of Illinois. Is it Illinois?
Illinois,
thank you. Illinois, and now he's the director of Georgia Tech's version of the Robotics Institute, which is maybe not the most polite way to say that, but that's what they call it too, so I'm okay with that. Maybe it's not good form to make fun of the other institutes.
Sorry, it's not like I get to speak after you.
But the thing that you should also note about Seth's career is his dedication to service to our society, our robotics society. So now he's the president-elect of the Robotics and Automation Society. He served on many editorial boards for IJRR, and now I think he's the founding editor of the Robotics Society editorial board. Is that right?
Sure.
It's close. And he served also on TRO's editorial board quite a bit. So with that, I think it's better to have Seth talk about all the great things he's doing than me brag about all the things that I do with him. So with that, I give you Seth.
Well, with the 5 minutes that remain, thank you, Howie, for the introduction, and thanks for inviting me to visit here. I get to Carnegie Mellon every few years, and it's always just a treat. You guys don't know how spoiled you are. Maybe you do. It's a great place, and the number of cool things that I saw in a short period of time, it's a bit overwhelming. It makes one want to go back and encourage one's colleagues to work harder. Spoken like a director. So let me say what I'm going to talk about today. So I have done a lot of stuff in the research world. I think not necessarily deep. Howie was kind when he said deep. A lot of it is quite shallow. And this is kind of another exercise in breadth at a shallow level, the talk that I'm going to give today. All the deep thinking that went into this, it's by these 3 guys who are here, most of whom are part of the great robotics diaspora of folks leaving the University of Illinois within the last 2 or 3 years. Ali Reza is now at Northeastern. Sunjo is now at Caltech. My student John is still at Illinois, but he'll finish within a year, and then we'll see where he goes off to. And then there will be no bat robots left at the University of Illinois. So this I think of as the farewell tour for the bat robot project. So, you know, buy your merchandise when you get the chance. I'm going to talk about this project really start to finish, not necessarily chronologically, because I think that's not an interesting talk, but more conceptually, and really with the aim of not talking about a robot just as an artifact, but trying to give some insights into how I've learned to think about these problems over time, which is not necessarily the right way to think about problems today, but it's the way I think about these problems now. And some sense of the evolution, you'll get some sense of my evolution in thinking about these problems by watching the things that I tried and failed. I'm sorry, I see random colleagues that I had forgotten had come to CMU, and so good to see you. Here's the first picture to motivate a lot of what I'm going to talk about. The picture in the middle, the movie in the middle, that's not ours. That's from the Smithsonian channel. When I think about biologically inspired robots, the way I think about that has changed a lot over the years. I'm not going to say which part of the spectrum I began on or where I finished on, but in the course of a long research career, I certainly have known well roboticists who have taken either one of these points of views about what it means to be bio-inspired. I have known a number of roboticists whose bio-inspiration is not any deeper than the guy over there who saw an animal do something cool and said, I should build a robot that does that cool thing, and publish it as a bio-inspired robotics project. And I have certainly known people in my life who have taken the other approach where they really want to replicate the biological mechanism almost down to the muscle fibers, not really, but approaching that level of detail. One of the things I like about the Bat Robot project is neither one of those is going to have a remote chance of being successful. And I'll talk more about why. But this, to me, is a chance to sort of explore the spectrum between the kind of very superficial inspiration and the very deep replication model of inspiration, and to try and figure out what are the right kinds of questions to ask, how should you ask them, where should you make the trade-offs. Those are the kinds of things that I find interesting about this project, more so than the particular artifact that emerged in the end that we tossed into the air and made it fly. Here are the first couple of questions. What's the right set of abstractions to use to think about this mechanism as it moves about in the world? And in particular, if I want to do something specific like fly, what are the right abstractions to apply to the task that I want to perform? Right, so what's even the right level of thinking about this thing? There are a couple of specific versions of that question. This is the first one. How much can I just ignore aerodynamics? Which is a question motivated by my deep ignorance about aerodynamics. I started this project. I lost a bet, but the student didn't have the courage to bet me when I made the bet, so I didn't pay. I really believed 4 or 5 years ago that if we studied the geometry of flapping flight, we could build machines that would do flapping flight, and it would be geometry, that would be enough to get this job done. There are people in the room already that are rolling their eyes at the naivete of that. But I believed it. It turned out, of course, not to be true. On the other hand, I know now that I don't have to understand aerodynamics at any level approaching what an aerodynamicist understands about aerodynamics. Right? And so what is the trade-off between geometry and then the dynamics that we think of as roboticists, the traditional kind of Lagrangian dynamics, which come into play because the wings have mass and they flap and they cause things to happen, but also aerodynamics. And what do you have to do on the spectrum of trade-offs between ignoring and solving numerical models using computational fluid dynamics techniques? Where do you need to be on that spectrum to get the performance that you want? Right, so there's a range of questions about modeling that has to do with dynamics, geometry, and the interaction between the two. And then there's a range of questions about control. Once you build the model for the thing, you design a trajectory for the thing, you toss it into the air, what's the control architecture to keep it in the air when it really executes that plan that you worked so hard to design? I mean, for sure, we're not going to do inverse dynamics. There's not a way to invert the dynamics anyway at the moment you write them down with aerodynamics terms involved. I'll show them to you at some point and you'll believe. Probably you already do. Linearization, that's tough. How do you do that? How do you choose the points along the trajectory? And is it even remotely realistic to think about things that way? And if not, are there some appropriate sets of low-order models that you could use that would get the job done? Right. So those are the kinds of questions that I find to be the sort of specific instantiations of this general rambling about bio-inspiration. These are the things that I'm going to think about. And then this is the way that I'm going to go about addressing those in the course of this talk. From the top, it's just sort of very high-level observations of the biological structure to figure out what is it about what this biological organism is doing that's relevant, and how can we extract something from the measurements of that biological organism that would be relevant and useful in the design. And after that, where do we go next? And the answer is, well, you get some high-level qualitative description of for example, the topological structure of the bones in that animal. Then you optimize something about the kinematic parameters of those bones. Then you optimize something about the kinematics of the flight, right? So just the first-order derivatives of what's happening to describe the motion of the thing. And if that's not good enough, then you go back and you start doing some optimization that takes into account dynamics and maybe aerodynamics. And then after all of that's done, you wrap some sort of control controller around it. That's the sequence that I'll go through, and I'll show you pictures of robots along the way from time to time. First, biology. So there's a bat, sort of. It's a cartoon of the bat. And the first thing to be said, every time you see a bat from here on out, it's not me that took the photograph of the bat. It's Kenny or Sharon, Kenny Breuer and Sharon Swartz. They're both at Brown. They study bats, right? They take bats, they toss them into wind tunnels, and they measure what they do, and then they share their data. So they're very kind to us in that regard. The blue dots that you see, they have often some correspondence to an anatomical feature like a joint, but also some of them are just places where you put the markers to do mocap, right? So there's a motion capture system that's going to analyze these bats at some point. And so this is as much a picture about motion capture and where to put the markers as about the design of the bat, but it captures very nicely the interesting structural properties of the skeleton of the bat and why it's hard, or why the system itself is complicated. You have revolute joints, you have ball and socket joints. There are about 40 degrees of freedom in a bat. Some of those degrees of freedom are active and some are passive. The skeletal structure itself, it doesn't say it here, but it's flexible, right? So as bats flap their wings, the wings bend in response to the pressure, the air pressure and the aerodynamic forces. And there's coupling between some of the degrees of freedom. So there's not a chance to build that thing as robot hardware and replicate the complexity of the biological mechanism today. Because today, if each degree of freedom requires an actuator, we don't have access to actuators that are small enough and powerful enough that this thing would have a hope to fly after you loaded it up with the 40 actuators. Right? So you have to obviously make some trade-offs somewhere and give something up somewhere. So where will that be? And the answer to that is moderately conspicuous. At the moment, you give names to the pieces of the bat that are anthropomorphic, right? So at the moment you call a piece of that robot an elbow or an arm or a digit, you almost immediately realize that this thing is just like the human hand in terms of its topological structure. And at the moment you realize that, you are inspired to steal from the robotics researchers who do human hand modeling and grasp planning and these kinds of things. And that's exactly what we did and what the biological people have sort of given the prelude to in their studies, which is to look at this not as a system with a lot of independent degrees of freedom, because certainly those degrees of freedom are largely not independent, but instead to look at this as a system that has some lower dimensional characterization of everything interesting that it might ever do, right? So maybe this bat could do all sorts of things that don't help it fly in any way, but when it's time for this thing to actually do flying, all the motions, all the states live on some fairly low dimensional submanifold of the state space of the 40 degree of freedom system. Right? So how do you get to that? Well, you do measurements. Can you see that? Okay, so that's a bat. Those are all the markers. This is a shot from underneath, right? So the idea is you convince this bat that he should fly down to the wind tunnel. You put motion capture system cameras underneath, and you measure the markers. And the way Kenny and Sharon did this was to actually solve the inverse kinematics problems and compute the joint angles for a bunch of joints in the bat as he flew along. They did something very much like principal component analysis that they call proper orthogonal decomposition. I think because Kenny's British, and so it should be proper instead of principal, but I'm not sure about that. And then they do loads of experiments because they're scientists, right? So they don't just toss a bat in a tunnel and measure it and say, there you go. They do enough experiments so that they can normalize out a bunch of variations over different kinds of bats flying at different kinds of speeds with different wing lengths, etc. Right? So they get back some information that should be, in some sense, canonical across at least some species of the animal that they're looking at. And when you do all that, you can create things that look like this, which are not really true, but they're close to being true. What do? You take the inverse kinematics, you get joint trajectories for the different joints, and then you do things like phase shift and multiply by -1 and scale so that you can show that, oh, look, these all cluster up in 3 ways, right? So once you notice during your principal components analysis that you get 3 kinds of motion that come out, you can do some normalization on the trajectories and overlay them in this way that really shows the structure. The periodicity, we don't mess with the period, just phase, for example, right? So what do these correspond to? They correspond to the 3 things that you might immediately think of if you were to just watch a bat fly, right? There's a set of joints that contribute to synchronized flapping of the 2 wings. There's a set of joints that contribute to the wing folding in and out. And then there's a set of joints that contribute to what the tail is doing. And biologists have really good words like asynchronous dorsal-ventral movement, which just means the legs are going up and down independently of the rest of what's happening. Yeah, that's enough to be said about that. So that tells us what the design goals are in terms of replicating the motion of the biological creature. In addition to that, the thing that comes out shouldn't weigh very much, shouldn't take much power, it should be small, there should be some structural capability. This is a sort of schematic of what the mechanism looks like, but don't believe that yet because you have not the right to believe that any of these things are the right dimension, but I have not the right to show you something without choosing a dimension for the figure. So this is a figure to sort of illustrate where we are in the design problem. Some kind of mechanism like this with a lot of parameters that we have to figure out what should they be. So first let me talk about the mechanism part because I think it's kind of cool. Here's the wing mechanism. I don't know how well you can see how this works. One more of these. This mechanism actually has 3 degrees of freedom, but only 1 really because the other 2 are coupled. You have a motor that goes back and forth which causes this wing to fold in and out. The mechanism in the middle is probably says on the next slide. It's what's called a 6-bar linkage or a Watt mechanism. And it's cool. One of the reasons it's cool is that it achieves this motion by coupling up the degrees of freedom in the right way, but also if you push normal to the face of these, either of these rectangles or these trapezoids, there's an ability to resist the force that you apply that you would not have if you didn't have the parallel linkage in place, right? If you just said, well, this would weigh less or be more efficient if I just had single links for the upper arm and for the lower arm, the answer is yes, it would, but also you would get torsional, you would not have the ability to resist the torsional forces that act when you flap the wing, and the wings would twist up and it wouldn't be a good thing, right? So this gives you some nice structural stability properties in the direction normal to the force that you get from flapping. The other part of this is much less interesting. It's the tail that just goes up and down asynchronously. And then here's a slide with a couple of videos that show you the degrees of freedom. On the top left, it's unactuated just to show how it moves, and then on the bottom right to show the independent actuation. All right, so that you could build that device in any size that you like, right? You could take that 6-bar linkage and you could change the links and the proportions of the different independent links to make all sorts of different things come out. You could change the offsets and the angles between the upper and the lower parts of the wings. The relationship of those folding angles is something you get to design. There are the fingers at the end that you get to design. Basically, you've got 2 kinds of things to do. There's all what you might think of as DH parameters that correspond to the lengths of the limbs and the angles between them. And then if it's going to fly through the air, there's a bunch of stuff that has to do with trajectories of the individual joints that drive the motion of this thing. So if you write that down as an optimization problem, you need to parameterize, and these are the parameters. Basically, there are 3 degrees of freedom that you get to control. I'm looking only at one side of the bat, right? So the other side is the same. You have a folding, you have a flapping, and you have a tail. So those are the 3 actuated degrees of freedom. You have 3 more that are unactuated in the sense that there are no actuators that independently control them, but they're coupled up to the first 3, and that controls the folding, and that's the purple ones. And then there's this pile of DH parameters to design for to make the shape of the wing geometrically accomplish what you'd like to accomplish. And that poses a design problem of build me a robot that somehow matches up with the shape of the biological bat throughout the course of the flight of the bat, right? So the evolution of the trajectories of something about that should match the evolution of the trajectories of something about this. And the somethings is, well, we've got all these markers on the biological bat. We can put virtual markers on the design target that we're creating. And now we have the ability to sort of match up what we'd like to see with what we do see. This is an example just to show you in a very exaggerated way, the kind of folding motion that a bat executes as it's doing something like hovering, for example, to eat something delicious. The bat that we used for all of our design optimization was this one, Tadarida brasiliensis, which I have to pause. It's much better to call him the Mexican free-tailed bat. He's more fun when you call him that. He's got coordinates for each marker. We do PCA to find the dominant modes, and we take into account the flapping motions. Kenny and Sharon gave us all of that data. And now it's not so difficult to do, right? You have real data that you observe from watching the real bat in the real tunnel. You've got synthetic data that you observe, or that you don't observe, that you predict from the design process and the optimization that you're doing. You stack those up into a data matrix in the usual way, time samples going down, coordinates going across, do a singular value decomposition of that, truncate, keep a few singular values, and you get a reduced order matrix that represents what you hope to be the low order model or the low order features of flight, right? And so I think we used 3 when we designed this. And now you have the possibility to just optimize, right? So you have a bunch of DH parameters that we stick in a vector called what? Called little a. We've got some trajectory optimization parameters. What do we do? Like many people, we say let's parameterize the trajectory as some sort of polynomial spline. I think we used, it probably says, 5th order splines here, so you've got a coefficient vector. That's all the parameters that you have to play with. For that set of parameters, you can construct what would be the trajectories of each of the markers. You can construct the truncated matrix from the slide before. And now you have just a norm minimization problem on those 2 matrices, the one that corresponds to the actual motion of the bat and the one that corresponds to the predicted motion of the design bat. Minimize for Frobenius norm, and to do that, you just dump it into MATLAB's fmincon. It gives you something back, and the something that it gives you back looks like this. Fake bat on the left, biological bat on the right. And of course, the biological bat on the right is not a real movie. It's a rendering that you get from playing back the positions of the markers triangulated so that it's got the same, roughly the same triangulation structure as what you have for the robot. Notice on the robot bat on the left that you have this Watt mechanism folding in and out to achieve the same kind of folding motion that you get from the biological bat. And in a good world, in a world of beauty and truth, this would be enough, and you would throw the robot and he would fly. But the world is neither beautiful nor truthful, and so you have to do more things. And I'll tell you now about those more things. It's reasonable to say that at this point, as far as we are able to do in the labs that I've worked with, this is the end of biology. Right? We've measured everything that we're able to measure of that biological thing, and we've done what we can with it. What we have not measured, because we don't know how to, are things like forces on the wing. Right? So when the bat wing flaps, there are dynamic forces. Those forces cause the wing to bend. The bat wings, and in fact our robot bat wings, are cool in the sense that on the downstroke, the flexible membranes fill up with air, and at the bottom of the downstroke they push the air out, and so you get the sort of aerodynamic amplification effect that happens. None of that is modeled, because none of that do we know how to measure on an actual bat. But you could instrument the bat up with all the kinds of things that you would need to measure that, at which point it's pretty safe bet that he would refuse to fly for you, right? So you have to instrument the bat in a minimal way so that he still wants to fly, right? And at some point he's really motivated to fly because you're the guy that's strapping stuff on and he wants to get away from you. But then at some other point it's just, I'm not flying anymore for you. And so the ability to actually measure things like forces and torques on the wings, not something that we have at the moment. So stuff that has to do with dynamics in the true sense of dynamics is not measurable at this moment, other than to infer it backwards by backing out something in dynamical models from motion capture data. Right? So there we are. Here's the prototype hardware, just to show what it looks like. It's very much like what you saw in the pieces, in the various slides before, in terms of the pieces of it. Here it is all put together. We played with a lot of different configurations of the hardware because And this is something I didn't think about as a geometry person, or I thought I was a geometry person. We learned, for example, that where you put the processor turns out to be important because the processor has a lot of mass. And if you put the processor in the wrong place, then you stall and fall out of the sky, or you nosedive and fall out of the sky. So balancing the sort of inertial payload of the robot turns out to be an interesting design problem that we solved by trial and error, not by doing interesting design approaches. There's a somewhat noisy video that I've stopped from being noisy. Same kind of thing. That's with the membrane on. I'll show you a couple more pictures. The membrane is cool. We found out that electrical engineers and aerospace engineers don't know how to make flexible membranes, but random undergrads from material science do. So we found 2 of them, and they made us this, and it's actually a really cool. It's very, very thin and very strong. And this picture, you see the guy in the bottom poking with a pencil. You get like 600% deformation, and it's very lightweight as well. So we get the deformation that we want. We get this nice sort of amplification of the aerodynamic forces, and it doesn't tear very easily. And even if it does, you see there are a couple of small holes. The tears tend not to rip out once you get a small hole, so that's nice. All right, now back to the problem of making it fly. Now that you've seen what it is, we stop with all the kinematic stuff that we observed, and we move to trajectory optimization using some sense of the dynamics. I need to show you at least a couple of equations. They're not complicated in any way. This is just a configuration parameter for this thing. There are 6 degrees of freedom. We have no direct actuation whatsoever that have to do with the center of mass, position, and the orientation of the body frame. There are a few more degrees of freedom that we don't have any direct control over because they're passively moving in response to the actuated degrees of freedom. And then there are the 3 degrees of freedom, or 5 if you take the whole left and right side, that correspond to the actuated degrees of freedom. It's convenient to break those into 2 chunks, the unactuated chunk and the actuated chunk, and to write the vector of configuration variables in this way, right? So that's nice. At the minute you do that, you can go to your favorite robotics book, and you can write everything. No, I don't know. Is that in the Howie book? You can go to your second favorite robotics book. It's in Kevin's chapter. You go to your favorite robotics book, but your 3rd favorite co-author's chapter, and you will find something that looks sort of like this, but not exactly like this. You'll see the M, the C, and the G, and the first thing on the right-hand side, that's Lagrangian dynamics. Right? And in a robotics institute, probably not interesting in any way. The last term on the right is the aerodynamics. And it's more interesting that it appears because I haven't directly represented to you the fact that it depends on the state of the robot. Right? So how fast you flap the wings has something to do with the aerodynamic forces. What does that mean? That means you are not going to decouple this in the usual kind of way. I mean, you can certainly rewrite it in this normal stacked form where you take the actuated and the unactuated degrees of freedom, separate it out, write the inverse, solve for this. But the problem is this thing is occupying all of the columns. You can't sort of factor it away the way you normally would in an exercise in your under-actuated robotics class, or use the Marx-Spong kind of approach to partial feedback linearization. You can do that for everything from here over, but not for this part. For the aerodynamics, here's a slide that's not meant to really tell you anything except that we thought about aerodynamics once. All right, so this is this is a really, really, really simple model of flapping flight. It's a quasi-static model, right? So, or quasi-steady model, they call it in aerodynamics, where you sort of model this as a fixed-wing aircraft at a fixed orientation and ask what would be happening if the aircraft were instantaneously flying in this way. And you compute a lift coefficient and a drag coefficient, and you push that through some standard equations, and you integrate over the wing that we pretend is a big rectangle so we can slice it up into strips, and we get something back that approximates the aerodynamic forces, right? And then we hope that it's not that important to what the robot really does, and that our controller will be able to fix it, right? So that's sort of where we are. What we're not doing is any kind of very sophisticated computational modeling of the aerodynamics, unless you're a computer scientist who thinks this is sophisticated. Oh, maybe you're all computer scientists and I've offended you all. I'm a computer scientist myself now, so it's self-deprecating humor. All right, and here's what we're going to do. We're going to do trajectory planning, which means we're going to find a desired trajectory for the actuated degrees of freedom, and we're going to basically play with that until the robot does what we'd like for it to do. And this is how we're going to do that. We take the kind of Jesse Grizzle kind of approach where you have virtual constraints and you try to ask, or you try to make the system evolve on a manifold such that that manifold is good, right? If you evolve on this manifold, everything good will happen. How do you do that? You apply the notion of virtual constraints to ensure that you don't leave it, right? So this is a very kind of high level way to represent that. For sure, once you pick some trajectory of the joint variables, you will have a trajectory that evolves on some kind of manifold. You can write down the definition for it. It's just this thing called S. And what you'd like is to make sure S has good properties like I don't fall out of the sky, the trajectories are periodic, and so forth. That is way too much mechanics, mathematical mechanics for what we want to do, unless this doesn't work, which it turns out it does not. And the fact that it doesn't work largely comes from numerical problems and computing derivatives in a way that's stable and robust. And so what do? We sort of turn that, well, and there's what happens. You get the same set of equations back with two more, and the two on the bottom are too simple to be useful. So what do? We treat this sort of like a PID control problem where we take the constraints that we want to impose, take a couple of derivatives, put them into what looks like a PID kind of framework, and now you can solve this thing at the top for the accelerations at the actuated degrees of freedom, and you get a set of equations that look like this that are not they're not worth understanding in a talk like this, except to know that once you have them and you stack up the dynamic equations all the way down to the desired trajectory, you can, once you have the desired trajectory, solve them from the bottom to the top, right? You can do numerical computations to, excuse me, to predict what that trajectory will be. You essentially have a forward model that you can compute numerically that takes into account some simplified model of the aerodynamics that I showed you before. And you have now the possibility, if you know the initial states, to compute what would happen if I change the parameters to that desired trajectory. I'm going to call those parameters at beta as beta. You can think of beta as being flapping frequency, phase offset between the wing folding and the wing flapping and those kinds of things. Everything that you might like to have to parameterize a periodic trajectory of wings goes into this thing called beta. And now it's another trajectory optimization problem. It's a heavier optimization problem than the one that I showed you before because of all the numerical computations that are going in. These are the kinds of things that you try to do. You try to make sure good things happen and bad things don't. You integrate the system dynamics. You compute gradients numerically. You enforce periodicity, and that's it, right? So it's again, we lean pretty heavily here again on MATLAB to do the work for us. And when you do that, you get behavior that looks like this. If you animate a simplified, and this is a 7 degree of freedom model instead of the full giant degree of freedom model that the actual mechanism has. And I forgot, what time do I stop talking?
As soon as you were tired.
I was tired at like 5 minutes in. I mean, I'm demonstrating endurance and perseverance here.
So sometimes people go all the way to 4:30.
I'm not doing that. All right, but I have time to tell you a little bit about the control design. So that's the desired trajectory, and that really is the way we were designing trajectories for a long time. Now the trick is when you toss the robot into the air to make him actually do what you commanded him to do. And if you really had a great model, and if you really optimized that model you would not need feedback control, right? You would have chosen the trajectory that bat robot wants to execute, that wants to keep it into the air, but we don't have great models. So for sure, we're going to need control to keep him in the air. And this is how we did that. First, I'm going to give you a quick recap of Poincaré maps because that's how we do it. It's not difficult at all conceptually. Mathematically, I find it quite heavy, but conceptually, I find it quite easy. If you take the state space of your system and you just slice it, right? So you set some variable equal to a constant and look at the projection, not even the projection, just the submanifold of that space defined by that thing equals to a constant. Then you can ask the question, when the robot passes through that slice of the state space, where is it? in that slice of the state space. And you take these continuous dynamics and turn them into discrete dynamics. And instead of asking, how does this thing evolve with dt, as dt becomes dt, you ask, what happens between now and the next time I come back to this piece of the configuration space? And this is the picture that you often see. None of this at all is unique to flapping flight. The people who did this, I think, most successfully and most visibly in the robotics community are the people who do legged locomotion, because it's the same kind of idea where what's interesting about legged locomotion is not necessarily what's happening all the time, but what's happening when the feet hit the ground. If you really can master the robot at the moment that its feet hit the ground, then you'll be in good shape. Right? So it doesn't really matter so much what's happening in this unactuated moment as the robot just kind of goes from one footfall to the next. For us, does it say it on this slide? Maybe. We look at the moment when the wing is at the bottom of its downstroke. Right? And so the question that we ask is, at the moment the wing is at the bottom of its downstroke, what's the whole state of the system? And then we predict, if we continue behaving as we do, what will be the state of the system the next time we're at the downstroke? And that's what the controller is going to use as its input signal, right? The difference between where we'd like to be at the next downstroke and where we predict we will be at the bottom of the next downstroke. How do you deal with that? You write down a Taylor series expansion, you throw away the higher order terms. This is it's very typical, usual kind of thing. Group the right terms so that you get a delta state variable. And then the answer at the end is, oh, look, it's a linear system, and it's linear in the control as well as in the state, not the control in the state, but the delta control and delta state. And if that's the case, then you can do something like feedback control, and in particular, you can do LQR control. And so what we do is we do LQR on the linearized Poincaré map, so that at the bottom of each downstroke, you look at the difference between where you are and where you'd like to be, and you update the parameters of the trajectory so that hopefully at the bottom of the next downstroke, things have improved. Right? There are so many lies in what I've just said to you if you take it as Seth really did this in the deep, mathematically rigorous way. But if you interpret what I just said to you as Seth probably hacked, and in the end it's a constant matrix and it's PD control, then there are no lies at all. So here are some flight tests. This, best thing about the University of Illinois, it's got this building that's called a stock pavilion, which in the day is filled with cows and in the night is a place to fly bat robots. So that's Ali Reza throwing the bat robot, and you see it actually, hopefully you saw that he gains altitude for a while and you back off on the throttle and you steer him gracefully over so that he lands, and it's nice, it's beautiful. I think that's the end. I don't think it's going to repeat. Here's a less beautiful one, just so you can see in real time what happens without the slow motion, the gracefulness of slow motion. So there he is. We spent a lot of money on nets that never were useful because the robot never hits the net. Yeah, so that's nice. And that was the end of Ali Reza's residence, I think, at the University of Illinois. He and Sunjo moved off to Caltech before he went on to be at Northeastern. And there are a bunch of things about that experiment that are potentially misleading if I just show you the video, having shown you first a bunch of mathematics. And so let me take a very short period of time to tell you some of the caveats. The most important caveat is the postdoc, the most important skill that a postdoc needs for this project is not the mathematical skills, it's the ability to match the initial conditions when throwing the bat into the air. Because if you decide to use LQR by linearizing about a trajectory, you need to be on that trajectory. And therefore, if you don't throw the bat robot so that he starts out with the desired initial conditions that match what you've optimized for, there's not any hope at all. And Ali Reza has never been willing to give me the videos that demonstrate his learning curve. It's like he came from the womb able to launch these bats. But I suspect there was a learning curve based on the invoices for repairing bats. So that's the first thing to know, is that there's a bunch of stuff here that is really, really sensitive and not robust at all. And at least in part, it comes from the combination of cheating on the dynamics, cheating on the aerodynamics, and also cheating on the control, right? We cheated across the board. So normally you say, well, I'm going to cheat on the aerodynamics and I will pay it back by using a more sophisticated control scheme. And we got to the limits of what our processors could do in terms of the control scheme quite quickly. And we ended up with, well, drop a constant gain matrix in there. There's a lot of mathematical explanation for why it's the right constant gain matrix, but still, in the end, it's constant, and so things are fragile. So in the last few, I don't know, since that period of time, we've tried to do the trajectory optimization better, and also to make the control better. And here's roughly the overview of how that goes. First, all the stuff that we did before with optimizing, we did not look at all at the tail surface. We treated the tail as kind of this thing to be ignored during planning but exploited during control, which is much the same as what commercial aircraft do. You have this tail that you can just sort of use independently to stabilize your airplane when it's behaving badly, and we thought we'll do that sort of thing, and so that's what we did. Now we've got a model that's better in the sense that it takes into account both what the tail surface is doing and what the so-called pronation of the wing, which basically just means, you know, how does the angle of the wing change when it flaps. It's not really just straight up and down. There's some curving that happens in the shoulders. We have low-order parameterized models of the aerodynamics, as well as parameterized model of the trajectory. And what does that mean? That means when you get down here, if everything is low-order polynomial models, you can compute the gradients of all the stuff that you need in optimization analytically, which means the optimizer will go much faster, and you can use things like collocation methods that will give you, much nicer results than some of the results that we got out. You get smoothness, all kinds of nice continuity properties that just are for free when you use these kind of approaches. Also, since we've considered the tail motion explicitly during the trajectory optimization, you have some hope that the control will be easier, and in fact it is. And we use here, really it's PD control, and we don't pretend that it's something else. It's really PD control. Here's the slightly more complicated model of the robot. It's still much simpler than the actual flexible infinite dimensional system, if you like, that we had before. Here's the part where we actually strap that robot onto a load cell and flap the wings like crazy and basically just measure aerodynamic lift forces as a function of frequency, because that turns out to be the dominant feature of the aerodynamics. Here's what that data looks like when you compare the real data to the predicted data from the model. The results that you see are not load cell models. And then we took the bat robot and we threw him and we measured his position using a Vicon system. I think it's a Vicon, some motion capture system. And the thing here that's cool, I think, there aren't that many cool things, but one of the cool things is the blue curve, which is the simulation results, that's sort of the predicted lift as the robot goes through its flapping motion, is not nearly as nice as the real data. Right? It is very seldom in life that your real system behaves better than your simulated system. I don't know why. I speculate that it's because of a bunch of unmodeled damping in the flapping flight that keeps the robot from bouncing up and down as much as it does in simulation. And the actual altitude simulations match up pretty well. Here's a video that starts, we're going to show this at IROS, so those of you who are going to go to Macau to see this, you can cancel. There's the simulated trajectory planning. So we plan here a real launch trajectory, right? Instead of hit the initial conditions, it's let this guy climb to the altitude that you want from wherever it's launched. And this is in a much smaller room. And also we learned how to place nets. And now the robot is hitting the nets, so that's good. And that's just the same results that you saw a minute ago in the IROS video. And I will conclude with that, just to say that, that's all the usual stuff you put at the end of the talk. But I think the part of this project, the aspects of this project that are interesting in retrospect, are much more the kinds of questions about the interactions between the computational demands, the accuracy versus the inaccuracy of the models that you use, the balance between how hard you work at control and how hard you work at trajectory optimization, how well you're able to couple the models that you use for planning with the models that you use for control in the overall context of the accuracy of those two. Those are the kinds of questions that I myself never thought about 5 years ago that I now find to be the interesting questions in robotics. I'll show you just maybe one other video. Yeah, so here's the other video. This is stuff that we started doing. It didn't go very far, but I like it because it shows that you could take the whole avionics pack off of the bat robot and put it onto a bat. And then you actually have the hope to start measuring some of the inertial forces that act on the bat as he flies. Not necessarily the aerodynamic forces on the wings, but you can at least get acceleration measurements that are now fairly accurate, both angular and linear, for specific physical experiments. And I think I'll stop there and answer questions for as long as Howie lets me.
Let's thank our speaker. Okay, questions? Martin.
You just mentioned that most you took out of this project was about the trade-off between computational.
Can you say that louder? I'm sorry.
The most you took out of this project, you said, was about computational demands
Mm-hmm.
and the trade-off. How much computational demand do you think does the bat have versus mechanical?
You mean the real live bat? How much computational demand is there? I don't know. It depends on how you measure computation, right? So if I give you the current en vogue thing is to give you a deep neural network. What's the computation? The thing that it does when I give you the network, or the 10 days of training that went before? So I don't know where the computational demand really lies in the biological element, but I know that he has the advantage of 1 billion years of, actually I don't know how many years, but a lot of years of bat evolution. I don't know the complexity of the bat brain. Yeah, so I honestly don't know.
My question was,
But you wanted to really make a point, like you wanted to drive something home. So I think you should thrust and parry now. Yeah.
how much bioinspiration is this really if you just take the kinematics and code?
It's exactly that much bioinspiration. So let me say that if you think I'm claiming something deeper than we were bio-inspired at the level of mocap kinematics and geometry, then you must not have been here for the first 5 slides. Because I'm not claiming any more than that. That's exactly what I'm claiming.
Maybe it's interesting to speculate about, maybe there's something in the design of bats.
Maybe there's something what?
Interesting in the design of bats and bat wings that helps in the control of light.
I don't even think that's speculation. I think that's a true statement. There is something interesting there. I'm not sure I'm getting the essence of it. Okay. No, so the guy in the back, because I saw him in Howie's lab and I hammered him for like 20 minutes, and this is your chance.
I was just going to ask if you could tell us a little bit more about what state estimation goes on this pattern.
Almost none. So we've got an IMU, and that's it. And we don't do much processing at all because the processor that's on board is really lightweight. And what we are not doing is using the motion capture system to give us feedback to the controller of the robot. He's just using onboard sensing for the last set of experiments that you saw. And for the first set of experiments out in the stock pavilion, there's no external devices of any kind. So it's just onboard IMUs and an altitude sensor.
And you're assuming the joint angles all follow the predefined trajectory?
Yes. Yes, I mean there are little tiny joint controllers that are trying really hard, and I don't even remember what's happening at the joint control level. But at the level of controlling the individual joint trajectories, I know that it's not. At best, it's a very low level linear controller, like PD at best. I'm sure there's no I. There might be a P and a D, but nothing more.
I would think that on a real bat it would be more like force control.
You know, if I had the money, we would have torque-controlled motors on this bat. Yeah, so I would imagine that real biological systems are not using position control on the joints to decide if they're flying well. I'm with you on that, but we don't have the capabilities to do that at this scale. And weight, payload limitations keep us from doing a lot of stuff that we might like to do as well. No, this guy. Yeah. No, the guy that's now looking over his right shoulder. Yeah. No, you're looking over your right shoulder again. Yes. The one pointing at himself. Yes.
Thanks. I would like to ask, at the beginning stage, you mentioned that you had some collaboration with biologists to
Mhm.
collect data. And after you finish the design of the entire robot, what's their feedback? Did your robot that gave them any insights on understand that better?
No, that goes under the unfulfilled promise section of our NSF proposal for this. We thought that there would be a really nice reciprocal relationship where we would give them something interesting that they could use. And I don't think we ever provided to them something that they said, wow, that's surprising and interesting. I think we were really the consumers of their science rather than vice versa. And I aspired, I thought, for example, maybe if we developed this kind of avionics pack that we could put onto the bat of the robot, we'll be able to, or onto the back of the actual bat, we'll be able to measure stuff that they could not measure. And they did measure some things that they had not been able to measure before. So maybe there was some insight that came to them, but I'm not aware of anything that came that was deep enough, for example, to be published in a Nature paper or a Science paper or something of that level. Okay, yeah, and then you, and then the guy in the back until Howie makes me stop. Yeah.
Okay, I might be asking something related to Hartman's question. First off, it's fantastic, it's beautiful, really.
Thanks. I think we should stop. let's call that a wrap, and
As a sort of reference, though, or comparison, right? There are people out in the streets and squares selling these wind-up things that fly around, and they seem to do pretty well, too. And
well, so if I understand where we are to this point was, that's really cool, but also toy makers.
Yeah, so, and it just reminds me of, so people were working on Lego Enclosure for a long time, and at some point, what's his name, came up with the passive...
McGear.
McGear came up with the passive system that walked, and I guess we already have an example of that, which is the toys that people are selling. So I'm just kind of wondering whether you guys have any insights about, like, did anybody stop and spend some time studying the toy, or do you have any ideas about, the differences, or I don't know, any insights you have related to that?
So I don't know the answer to, did anybody study the toy? It could be that Ali Reza designed all of this based on Festo's latest design. So there are some differences that are more in the promise than in the realization. One of the differences is the flexibility of the wings of our system, as opposed to the rigid flapping flight that you see on the toys that are out there. The ability to independently fold the wings gives this guy the opportunity to do controlled maneuvers in the air by changing the symmetry of the flapping motions in a way that I thought would lead us to, I've got another insight that sort of here's what we did wrong that I'll tell you in a minute, that I thought would give us the ability to do really aggressive maneuvering, controlled aggressive maneuvering, right? Not just sort of uncontrolled ballistic motion, which I have a video that shows. And we haven't succeeded to do that yet, but John doesn't have his PhD thesis yet, so I'm still hoping that we'll get some, he's doing some trajectory optimization for more aggressive maneuvers, but whether or not we can really do that in a controlled way is hard, because here is where the state estimation matters, right? I don't know that we'll be able to do the state estimation that's required to do those kind of controlled aggressive maneuvers on a real platform. So the flexibility of the wings and the capability that you get from that should be the two main things that come from this work that's better than the toys. Yeah, beyond that, I mean, they fly pretty good. The Festo bird is really a good thing. I mean, it's really an impressive machine. So I don't know that it goes much beyond that. I will say this about, and on the list of naive things that Seth used to believe that led him astray. We were motivated to do this in part because we wanted to be able to get, bats are amazing, right? They do these aggressive maneuvers, they can invert themselves and perch. A lot of really impressive maneuvers aerodynamically. And we wanted to do that. And the way we did that was to design a robot based on watching bats fly in straight lines over a wind tunnel And so I think we went astray in the very, very early part of the design by choosing the kind of motions that we would use to motivate both the kinematic design in terms of the structure and in terms of the trajectories that we began with in the optimization part. Yeah, I won't say any more self-deprecating things about my naivete at this moment, but I will share that. So.
Yes, so I was wondering, are there any interesting effects introduced by the elasticity of the silicon membrane that is attached, that is coupling everything together?
So I mean, the answer is I'm sure that there are, and I have no proof that there are. Right, so what we haven't done is any kind of experiment, for example, that compares the performance of this device with a device that has some sort of less flexible membrane or non-flexible membrane. And so I don't have any quantitative answer for you. And part of the reason for that is the less flexible membranes also have different weight and mass distribution, and so it's hard to isolate exactly what's the cause and effect between, for example, aerodynamic lift as a function of the flexibility of the wing. I don't know how to do the experiment, so we haven't.
So maybe the frequency components in the output signals that you get from measurements can reveal if there are some frequencies that you weren't expecting and were there.
Which frequency measurements?
So if you were to be tracking position locally on the body for somehow, and you were to do an FFT on the data,
Yep.
then that FFT could reveal some components that you didn't want to be there, but they're still there.
So I agree, and I used to be an electrical engineer, so I like Fourier transforms deeply. And it will tell you something about the flight, but I don't know how it tells you something that you can attribute directly back to the flexible structure of the wing. Unless you did some sort of harmonic analysis on the wing mode vibration, which I don't know that we have the skill to do. But if you know how, talk to me afterwards, because I think that sounds cool. And I can't, at this moment, I can't visualize how to do it, but I think it sounds like a cool thing to think about. Well, I told the guy in the back next, and then I'll come back to the front. Yeah?
Yeah, did you ever take your bat and recreate the initial wind tunnel emission capture tests to see how closely the trajectories and the points that you were tracking?
We did not. Yeah, no, we did. And I don't know that we even hope to do that. Because in the end, the trajectories that we executed were different than the bat trajectories, and certainly the speed of the trajectories would have been different. And also certainly we have no promise that this bat will be able to fly at the same speed as the speed of a biological bat. So we didn't do that. Also, I'm pretty sure Kenny and Sharon are not keen on us throwing a machine into their biological habitat for bats. So we did not do that experiment.
Well, to think about the flexible membrane, when we took the aerodynamic with the force.
Yes.
It looked like the experiment, you got more aerodynamic force than you predicted.
Yes, we did.
And you talked a lot about this.
Just in a narrow band of frequencies,
Yeah, so
right.
Frequency
Yep.
is more force than you expect. You usually get less force than you expect.
Yep.
And you talked a lot about this like amplifying effect from flucture.
Yeah.
And then that's not in your model anywhere.
Yeah.
And so like is that what we're seeing in that little blip on that graph?
So that, again, the answer to that, the honest science answer is we didn't do an experiment. I have not the right to say it, but I'm perfectly happy to believe it and would love it to be true. So that's the sort of religious dogma side. That seems to be a legitimate explanation that I'm not willing to say without having a bit more evidence.
And I think a harder version of that is you told us that the flexibility and the amplification was like the key part of how bats were flying.
I'm not sure I said key part.
An important part. And then it doesn't show up anywhere in your model, but your model flies just fine. And then you didn't predict it, and so you're following a trajectory that doesn't necessarily take advantage of it.
Yeah.
But if it's actually there, then it's.
So I'm not willing to sort of take I'm not willing to accept those things. No, I'm not willing to state those things as being really well justified, because there's also a bunch of other stuff that we didn't put into the model. Right? And so it could very well be that there's a bunch of stuff that makes the robot want to fall out of the sky that's being nicely canceled out by this amplification effects of the flexible wings, and we didn't test any of that. And so I'm very hesitant to start drawing attributions between what contributed what in all of this. But the story that you're telling is one that I would really like to be true and that intuitively I agree with.
the challenges of scaling up such a system?
Would be the what?
What would be the challenges of scaling up such a system?
Oh, yeah, the physics, laws of physics won't let you do it because, I mean, it has to do with Reynolds numbers, right? I mean, you can look at things that flap their wings and fly, and you don't see any big ones. Right? It just, there's, I don't understand the aerodynamics well, but I know that aerodynamically large flapping flight doesn't work, and tiny flapping flight is much, it works much better, let me say that. Yeah? You have a follow-up question? So, like flying elephants, no. I mean, if we're going to like, I'm sorry, go ahead.
Another question is, did you test the bat for turbulent conditions?
No, God, no. That's an expensive bat. We're not going to throw it into turbulence and see what happens. I know what would happen. And we would buy a new bat. No, we didn't test the bat in kind of adverse circumstances. We tried to make the environment as friendly as possible for the bat robot.
Two more questions. There's one in the back and then one there.
You choose. Yep.
All right. So in my experience, all the robots I've used, feedback linearization requires really high torques.
Oh, we do not do feedback linearization, right? So I hope I didn't lead you to believe that we do. We do linearization. Yeah.
I see. How did you keep the, how big were the torques? Is that ever an issue to keep the control?
I'm sorry, I just can't hear you.
How did you keep the torques down in general?
Oh, well, so the easiest way to keep the torques down is to buy motors that only have a limited amount of torque. And that's what, you know, we bought the most powerful motors that we could buy, and then we just tell them flap like hell. So there's not really a moment when somewhere in the control design it says, oh yeah, back off the wing torque. I mean, that's not happening very often. I mean, it's pretty much turns out to be just go at it.
And one last question.
So, about this whole discussion about buying inspiration, so robots have different sorts of actuation than animals.
Yes.
In this case, the bat. So, how can you make a connection between the geometry, the similarity of geometry and performance or dynamics? And does it make sense for the robot to mimic the trajectory of an animal?
Mm-hmm. So I think, if I understand your question, is that hour-long talk. Does that make any sense? I mean, roughly that was paraphrased. I mean, yeah.
Does it make sense?
So I'll say that I feel that it made sense. No, so it's a legitimate question. I think it's a good question, and I think a lot of that comes back to my original belief that geometry was all that you needed. I still believe that there are some forms of locomotion for which geometry is the be-all and end-all description of the motion. I might be able to get somebody to disagree with me, but I bet not. Snakes, yeah. So there's a guy over here who has made a really nice career of. It's pretty good.
I appreciate your validation on your.
Yeah, by relying on the fact that the geometry of the motion is the thing, right? And I thought this would map over to this particular example, and it did to some extent, right? I mean, it's not like the trajectories that came out were crazy different from what we began with, and it's not like we took the model that we optimized, right? So we optimized the kinematic structure, and we changed it a little bit. Over the course of 6 iterations, but not much. And a lot of the changing just was to do with the aerodynamics of the tail and making the tail a bit longer so you get more stability in the control mechanism. So a lot of the design that was based on just the geometric properties turned out to be fine. So I think it's interesting to ask the question, Seth, what you just said seems to make no sense, which is not really a question, but I'll give you that. I find a more interesting question to be at what point does it stop making sense, right? And is there some bunch of stuff that you're doing for which these inspirations make sense in this way? And it's not unrelated from the earlier question about biological inspiration and do I have a right to use that phrase, right? I feel I do have a right to use that phrase, but not beyond, you know, slide 17 or whatever it was. So I don't know if that answers your question or not. So.
What's interesting is that for the snakes, I think that the geometry goes a little bit further because we don't have
Yes.
dynamics. And I think the big difference is with the snake robots, if you go twice as fast, you move twice as far.
Yeah.
And that kinematic relationship, as long as that's true, we can get away a lot more with geometry. But geometry is never going to be the end-all explanation for everything. Hardly the case.
Also, snake geometry, much more beautiful than bat geometry in the end. It's really beautiful. It is.
There are other systems. Okay. So before we go away, I'm just curious, because this, I got an idea from your question. You know, it's rare we have these times together as a group, but I'm wondering, would the students be interested if maybe once a month or once every 2 months we dedicated this time slot to a discussion like the role of biological inspiration versus non-biological inspiration? So this is a show of hands. How many students would, and young faculty too?
Wait, I didn't understand the question, and I know I'm not a student, so it doesn't matter.
You're important too.
You're asking the whole slot, not this time period of questions, but you mean instead of a talk,
Instead of a talk,
at 3:30 to 4:30 or so, we have a discussion.
correct, that was my question. Would you be interested in doing that once, maybe every 2 months, instead of an RI seminar, to have a discussion and you all can talk and we can watch? So just show of hands, who's interested in that? I appreciate your honesty. Okay, we'll figure something out. Okay, thank you. All right, so with that, one other announcement. Is there a post-seminar reception in the atrium now?
There's the next slide.
TG. I confuse those two again. I'm not old. So for those of you who care, there's something in the atrium, it's a TG. So if you want to keep talking about robot stuff with Seth, you can go there. And let's just thank Seth one more time for